Okay, hi everyone. Before we get the slides up, I do realize I'm the last thing standing between you and happy hour. So I'll try to go fast. As Emilia mentioned, the content of my talk is TF.data, which is TensorFlow's API for input pipeline. So let's motivate the talk by asking ourselves, why do we need an input pipeline API in the first place? Why not just load the data into memory, say using NumPy, and process it? Well, there's a number of different reasons why having a dedicated input pipeline API is a good idea. First of all, not many data sets, or not all data sets, fit into memory. And given the audience here, I would actually expect the common case here is that your data sets do not fit into memory of a single or multiple computers. But even if they would not fit into memory, you could imagine preprocessing them with a framework like, say, Apache Beam, and then storing the preprocessed data and then just streaming it into your machine learning computation. So why do we need to do that kind of live as we're doing the machine learning computation? Well, the reason for that is it's not uncommon for the preprocessing that needs to happen during the machine learning computation to be randomized in some way. For example, you want to shuffle your data to avoid biasing your training towards the order of your data. And you might also want to apply some randomized transformations to your data, say if you're doing image-based training. Another reason why having a dedicated input pipeline API helps is that it allows you to decouple the content, the intent of your preprocessing from how the preprocessing executes, which, as I will get to, will allow us to efficiently utilize the underlying hardware for the preprocessing. And it also allows us to scale the preprocessing from a single host to multiple hosts, because, again, the way the preprocessing is executed is independent of the API in which we expressed it. So for all those reasons and others, we designed TF.data, TensorFlow's input pipeline API. And I think of TF.data as the API for the ETL process of TensorFlow, where E, T, and L stand for extract, transform, and load, respectively. TF.data provides you with facilities for reading the data either from local or remote storage and parsing the file format in which your data is stored. It then also provides you with building blocks for applying both domain-specific transformations, such as text vectorization, image transformations, or video temporal sampling, as well as domain-agnostic transformations, for example, shuffling or batching, which are both best practices for machine learning. And last but not least, TF.data also provides you with a functionality for efficiently transferring the data onto the accelerator in case you're actually doing your machine learning computation on a hardware such as GPU and a TPU. And the reason why doing the the non-machine learning computation done through TF.data as efficiently as possible is illustrated by this graph on the right, which suggests that there is this opening performance gap between the computational resources available on the CPU host as compared to the accelerator attached to the host. Basically, the GPUs and TPUs attached to a single CPU host are getting much faster than the CPU compute power available on that host. So let's just jump into an example of what a TF.data input pipeline might look like. And in this example, I'm illustrating something that could be an idiomatic input pipeline for doing image-based labeling. TF.data provides two sets of building blocks. The first building blocks we call TF.data sources, and they basically define where is your data coming from. And once you create a TF.data source, what you get back out of it is a TF.data dataset, which you can think of as a stream of elements contained in that dataset. And once you have a dataset object, you can apply transformations to the dataset kind of in a functional paradigm, and the transformations give you back a modified dataset. So a map transformation is kind of meta transformation in the sense that you can customize it yourself with a function that defines how the elements of the input data sets should be transformed to produce elements of the output data set. I'm eliding the details of the preprocess function here, but the preprocess function could, for example, parse the format of the individual records in the file, and assuming it's an image, it could then perform some cropping or decoding, say if it's a JPEG, and applying distortions to the image. Another example of a TF-data transformation is a badge, which combines multiple input elements into a single higher dimensional output element, kind of representing a common practice or common best practice for training. What I haven't mentioned yet is that TF-data is the recommended API for doing input pipeline with TensorFlow, both in TensorFlow 1 and TensorFlow 2. And it has a tight integration with TensorFlow APIs for doing machine learning. In this case, we're looking at an example of the Keras API. So you can just pass a dataset object straight into the model fit method that would perform training on the data set represented as the TF-data object using 10 epochs. So next, what I want to talk about, because I feel like the audience here is interested in performance and scale, I want to talk about best practices for building performant input pipelines and how these best practices translate to actual applications or uses of TF-data. So if you were to do your input pipeline processing and your machine learning computation kind of naively, you might end up with execution that looks kind of like this, where as you're pre-processing your data for the current step, your accelerator sits idle, and then when you're training on the data pre-processed for the current step, then your CPU sits idle. And very common standard trick to improve the efficiency is to use software pipelining. So do pre-processing for the next step while you're doing processing of the current step. In TF-data, we provide a transformation called prefetch with optional argument buffer size that allows you to decouple the data producer from the data consumer using an internal buffer for the intermediate results. And that's all it takes to apply the idea of software pipelining either at the end of your input pipeline, which is the most common use case, but in general, in any place inside of your input pipeline, in case there is multiple stages of the computation that may make sense to overlap. The second common practice that we recommend for TF-data users is to do parallel transformations of your data to do transformations of your data in parallel. So in the example we were looking at earlier, we're processing the elements of the input data set one at a time. But if there are no data or control dependencies between the processing, you can just parallelize the processing, thus reducing the step time needed for the pre-processing itself. And in order to apply this best practice to your input pipeline expressed in TF-data, all you need to do is to set the additional num_parallel calls argument for the map transformation. And it will have the intended effect of pre-processing multiple elements of the input data set in parallel using background threads, and again, using an internal buffer for coordinating with the consumer of the data, in this case, the badge transformation. Last but not least, if the pre-processing, the data compute CPU is not your bottleneck, what could be a bottleneck is the actual I/O. Say if you're reading from remote storage, the bandwidth that you have might be, for a single file, might have some limitations, or perhaps parsing of the data format could be a limitation. And similar to parallelizing the transformations, parallelizing the data extraction is a common best practice that we recommend to TF-data users. And the way you can apply this to TF-data input pipelines is through the num_parallel readers argument that all TF-data sources support. And that will have the intended effect of opening multiple files, assuming that your data is sharded across multiple files in parallel, reading in parallel, processing or passing the format in parallel, and then interleaving the output from those files in either a deterministic order, which is the default behavior for reproducibility, but you can also optionally set that you don't care about ordering, in which case your input pipeline might actually run even faster. What I didn't mention here is that the specific values that you provide to either the prefetch buffer size or the number of parallel calls do matter. If you set these to be too small, your input pipeline might not run as fast as it could. And if you set these to be too large, it actually might not run as fast as it could either. The latter might be a little more surprising, but the reason for why setting these values to be too large would result in suboptimal performance has to do with things like inefficient thread scheduling or excessive memory usage and memory pressure. And for the initial period of time during which we actually introduced this functionality, users were kind of responsible for figuring out what are the right values for these. But earlier this year, we've added support for specifying a special value called autotune, which basically communicates to the TF.data runtime that it should figure out what are the optimal values for these arguments. And the TF.data runtime then uses a reinforcement learning-based algorithm as it executes the input pipeline to kind of converge to the values for these arguments that give it the optimal performance as measured based on actually monitoring the performance of your input pipeline. Related to the point about determinism that I made earlier, I want to call out the existence of the TF.data options object, which is a mechanism through which you can set global options of your TF.data input pipeline. So, for example, controlling whether your input pipeline should be deterministic or not, how to collect statistics, which sort of optimizations that are not enabled by default should be enabled, as well as control more advanced aspects of your input pipeline, such as whether to use a dedicated thread pool for execution of the background threads, or something called intra-op parallelism, which basically controls whether the individual ops in your computation should try to be parallelized or not. And the way you use you set the options for TF.data dataset is by creating an options object, setting the options you're interested in, and then using the with options transformation that gives you back a data set that has those options set. And these apply globally to the dataset object. All right. And this is actually my last slide. I also want to call out the existence of the TFDS project, TensorFlow Datasets, which is independent of TF.data, but it's based on TF.data. TF.data itself, the motivation behind it is to provide TensorFlow users with reusable building blocks for building input pipeline that fit their needs. But if you're looking for a quick way to get started with existing data sets, you probably want to take a look at TensorFlow datasets, because TensorFlow datasets provide, I think at this point, 50 plus different standard data sets, an already pre-made input pipeline that you can use kind of off the shelf for your experimentation. And the way you use it is it's a separate Python library. The list builders call allows you to enumerate all the different data sets that are available. These span text, image, video. And then through the TFDS load, you specify the name of the data set that you're interested in. In this example, it's the MNIST data set, and whether you're looking to get a train data or test data. And what you get back is an instance of a TF.data data set that you can either further customize yourself, or you can, through something like the take transformation, inspect if you want to kind of get a sense for what the elements in the data sets look like. Or you can immediately just pass it into Keras and your model and perform computation from there on. All right? Happy hour.